Thank you. Thank you for having me at the conference. I really look forward to this weekend and I already enjoyed the previous talks. My name is Tammo Dijkema. I work as a scientific software engineer at Astron, the Netherlands Institute for Radio Astronomy. And I did this work last year together with the team mentioned on this slide. This was actually the first project I did on meteors. And in fact, the proceeds in 2020 were the first time ever I observed a meteor. But the last year I've learned a lot about this field and I think it's a really interesting field. Okay, to get started, I ask you to have a look at this picture and think about what you see. Well, the title says it already. Everyone who has an Allsky camera recognizes this picture. You have the horizon at the edges and zenith is straight up. Also, you may recognize the galaxy, but also this is not really a normal Allsky picture because, well, for example, I don't see a Big Dipper here or any other star I recognize. You see and that's because this is a radio picture. This is somewhere between 30 and 70 megahertz. So this is in fact the galaxy, but all these little dots here, they are other galaxies far away, and you see the radio emission. I labeled a few very bright sources. This is Cassiopeia A, Cygnus A, radio galaxy. This is supernova remnant, and this is the bright galactic emission, which is higher near the center. If you don't know this map yet, that's because that's not strange, because it's from LOFAR, which I will talk a bit on later, and that's a radio telescope which has existed only 10 or 15 years. Okay, so why would you look at meteors at low frequencies, at radio frequencies? Well, meteor trails reflect radio signals, which is a fact that radio amateurs use to make contacts with other radio amateurs over the horizon. That's a fun application, but also for example, the Brahms project or other meteor radar projects use that to get the orbits of meteors. But also in 2014, another low frequency telescope, the LWA, reported broadband emission from meteors. And here's an image they made with their radio telescope. And they saw this broadband emission, didn't know really what it was. And they hypothesized in a lot of papers they've published since that this may be intrinsic emission from the meteor trail, from the ionized air. Now, LOFAR is more sensitive and has a higher spatial resolution than the LWA. So we thought we would try this also with LOFAR. In fact, this was already also suggested by the people from the LWA in one of their papers. Okay, what is LOFAR? LOFAR is the low frequency array. It's a European radio telescope with 50 stations all over Europe. It is sensitive in 10 to 90 megahertz and well, also until 300 megahertz. Each station of LOFAR consists of a few hundred antennas, and in particular, these antennas in the low band are used for this project on meteors. So this antenna works from 10 to 90 megahertz. It looks like a stick on the ground, and that's exactly what it is. And in fact, the stick is not the thing. The cables that hold up the stick, those are the actual antennas. Now, in the normal operating mode, LOFAR has a field of view of about 5 degrees, which is way too small to catch meteors, or you have to be really lucky. But luckily, there's also another instrument attached to the antennas, which is aardvaak, which is 500 antennas, almost 600 of LOFAR in an area of around 1 kilometer. They are correlated individually. That needs an enormous computer. The data rate from the antennas is about 60 gigabits per second, and the output is still 500 megabytes per second. But this can make all sky images with the antennas on this area. And just here's another pretty picture of this area. Here's a kind of island, we call it a super terp, with thousands of antennas on it. These are the antennas we use, the little dots. And also you see outside of the island, there are also some stations. And this was the instrument that was used for our main result. Now I could talk at least an hour about LOFAR, but let's just present the main result. The main result, we imaged in one night of the Perseids 2020, we imaged 200 radio meteor trails. You see one of them over here. This is a radio meteor trail on a resolution that hasn't been imaged before, ever, I think. So 200 radio meteor trails in only one night. We were hoping to catch only a few in one night, but there were 200. And we were very lucky to have the CAMS project, the CAMS Lux project, and it was a clear night that night. So we have optical counterparts for all of these meteor trails. Then we thought we would repeat the experiment during the Geminids of 2020 and the Quadrantids of 2021. And to our surprise, we hardly saw any radio meteor trails. And that's not because it was cloudy, but clouds do not block radio waves. So I will try to explain that a little bit later. It was actually helpful to not see anything there. But first, some more zoom-ins of results of some of these 200 radio trails. Here's a nice one in the Northern Galactic Spur. You see here the meteor. Here a zoom in of the meteor, and here you see the CAMS trail, the trajectory from optical observations overlaid. It starts at the cross and then goes that way, and you see that the trail really matches perfectly with the optical trajectory. Okay, another one, a very nice meteor, and another one. I think it's a Perseid, and another Perseid. And as you can see here, we made a movie of this one. Let's see if it starts. You see that the trail gets blown apart by the upper level winds. And this trail lasted on the sky for about 2 minutes. So now the big question is, what causes this emission? What makes this radio signal? Could it be a specular reflection, as all the radar investigations use? Or the radio amateurs use, or could it be intrinsic emission, as the people from the LWA think? Or could it be a specular reflection of celestial radio emission from a reflection of radio sources in the sky? So let's go into all three of these. Could it be a reflection of a man-made signal? Now we did some kind of spectroscopy in the radio wavelengths. So these are a lot of channels, and in every channel you see the trail. Sometimes it's weaker, sometimes it's extremely bright. So we're quite sure that over here, this is so bright, this is a reflection of the Brahms. This is exactly the Brahms Belgian radar system. And in this channel, the meteor is the brightest thing on the sky, and it messed up our calibration actually. But also in all of the other channels, here's a spectrum. You see some of them are crazy bright. That must be man-made reflections, narrowband. But normally man-made signals are not this broadband, and you see even a slope in the spectrum which is typical for celestial sources. So probably it's not just a reflection of man-made signals. So could it be intrinsic emission, like the people from the LWA think? Well, maybe. But we're not convinced yet. These are images from the LWA. We don't know yet, but if there's a better explanation, we'll go for that. And well, what causes the broadband emission? I mentioned already, we observed during the Perseids, Geminids, and Quadrantids. We saw lots of Brahms radar reflections. We saw 200 reflections of the 200 radio trails in the Perseids, only very few in the Geminids and Quadrantids. Okay, and optical counterparts we didn't have for the Geminids and Quadrantids, but I trust that there were a lot of Geminids and Quadrantids, as there are every year. Also confirmed by the Brahms reflections. So here's a very nice one of the Quadrantids meteors. So we did catch some, but very few. So could it be a specular reflection from a celestial source, from a radio source on the sky? So we have simulated, and we know that it's not Cygnus A or Cassiopeia A, which are the two brightest sources in the radio sky. But also there's this blob here, which is the bright radio emission near the galactic center. And during our Perseids observing window, we saw that the galactic center was partly up. And also a little bit below the horizon, you could still, due to because the meteor is 100 kilometers high, you can look a little bit below the horizon. And during the Geminids and the Quadrantids, the galactic center was below the horizon. So that could be a very good explanation. So that's really our hypothesis, that we are seeing the galactic center. This does not mean that the people from the LWA are wrong, because they are looking at extremely bright fireballs, and it could still be that those do have some intrinsic emission. So a bit more about our setup, because we had time on LOFAR. We thought we would match with as many other instruments as we could get. We have an Allsky camera in Dwingelo, operated by Felix. You see a very nice match here, also with a CAMS trail and a Meteor trail over here. It is, right? This one. So that's a nice match. Also, we noticed that there was an infrasound match with an infrasound station. This will be published later, I think, by Jelle Assing from the Royal Dutch Institute, Royal Netherlands Meteorological Institute. This matches very nicely with CAMS and LOFAR, and they can also measure speeds with this technique. Well, to show a bit about the CAMS results, that night was a very nice night for the Comet Lux project, which is the optical project with, I think, 73 cameras operational in that night. You see in gray, you see the field of view, and these circles here are centered around LOFAR. This is where LOFAR is, in the north of the Netherlands. Unfortunately, there's not a very good coverage in this area of the sky, which is why my all-new Meteor camera is pointing right that way. So next time we do this, we will have a bit more coverage even, but still. Also, I'd mentioned the Brahms project already. Here's a very nice overdense Brahms reflection. And a head echo, I think, but that was at a different frequency, so that's not from the Brahms radar. And unsurprisingly, the meteors which had Brahms reflections were all quite low in the south, which you can see on this map. Brahms is, I didn't draw it, it's here and here, and we are here, so those matches were all around this area. Now we had 200 detections, which means we can do some statistics. The radio flux, bright in radio versus bright in optical, and there's a correlation between that. Both are not very accurate. Very bright meteors in CAMS are often saturated, and our flux calibration is not optimal yet, but there is a correlation like this. Also, bright meteors, the trails of bright meteors last longer on the sky. This is how long it lasts. Some lasted minutes and some only 2 seconds. There's one statistic I really liked, and that really stands out. We measured by hand the trajectory of the radio trail. And the radio trail starts around 100 kilometers, whereas the optical trail really starts higher on average. So that means that must mean something about the height at which the air ionizes enough to become reflective. So we did a lot of work. There's a lot of work still to do. We would like to repeat the Geminids and Quadrantids observations with clear skies. So good luck with that. We would like to model the specular reflection of the galactic extended emission. We can do that theoretically. It's just some programming work to do. Also, we would like to repeat one of the another mode of LOFAR where we have basically infinite time resolution and infinite frequency resolution, so that we can catch a spectrum of a meteor. But that means that we have to catch a meteor inside a 5-degree beam, so we would have to have a lot of luck or a lot of time on sky. Also, we did measure the polarization, but we haven't looked at that yet. So that's all for now. While I hope there's time for questions, and you can look at this movie of the meteors, which are annotated. Thank you for your attention.